let's try to combine the three elements. We call it the Fabry-Perot etlon. Yeah, let's consist three parts of the system. One is interface A. Second is a homogeneous cavity. The third is interface 2. So, if we see from the point of scattering system, what is S11? S11 is B1 over A1 when A2 is 0. So, 11 should be B1 over A1 when A2 is 0. So, it will be, since we reasonably assume the index in the middle is higher than that on both sides. So N2 is larger than this side, so the reflectivity here is minus value. Okay. So first it will be R minus R11 because there is some first you have some power direct reflect from the interface. So okay. So the first term is minus R11 because somehow will just directly reflect the interface. And the sun will first pass the interface. Propagate F. Reflect it again. So this is T1, 2. Okay. Exponential minus J beta L R22. Exponential opposite because it's for transmission of still minus J beta L. And T1. Okay, so the second term should be T1, 2 times T2, 1. So let's just let this 2T to be the same. That to be T squared. Exponential minus 2J beta L because we times it twice. And the times R22. Okay. However, it's not 100 of light will be transmitting this interface here. It might go his again, R11. So, we need to consider the probability. Some of them goes to R11 and again for a second round or for infinite round, at least in some moment it leaves this interface. So this whole term should times a summation of this whole round trip R11, R22, R11, R22 exponential minus J beta 2L, 2 beta L. The whole term for n times. Yeah, because you can go living, some of them living it, but some of them keep going in any other route. So this is an infinite series. It should be 1 minus A, the ratio. So the result is minus R11 plus 1 minus R11 R22 exponential minus j to beta L, then t squared exponential there's R22 here, R22 exponential minus j to beta L. So that's how this comes out. Yeah, so it is problematic to generate a lossless a combination of system with scattering field. What if I add another segment here? It will be pretty difficult. Yeah, you need a rather difficult procedure to make this combination. Okay, so the S11 is written like this. If the interface is lossless, we can further reduce that put times the denominator and put it back, and let the T1 squared as 1 minus R2 squared. Then it can be simplified like this expression. Okay, then the S2 and S21 and the S22 is similar. We just draw what does it happen. So S12 is the B2 over A1 when A2 is 0. So you have sum here. So it has a T. Then propagating exponential minus j beta L. And leave this system. So this is T1. So this is T1 here. And this is T2. Alright. So it will, if there's no iteration, it will be T1, T2, exponential minus j beta L. But you need to consider it might circling around again for unloose. So this will be also the sigma of n is equal to 0 to infinity R1, R2 exponential minus 2j beta L with n rounds. So it becomes the denominator here. So it is T1, T2 exponential minus j beta L divided by 1 minus R1, R2 exponential 2j beta L. For the S22, this is rather simple. You just switch all the number 1 and 2. You will directly get the answer. Okay. So how do we describe lacing with a Fabry-Perot cavity? Lacing means if there is no input, you don't give any light input to the cavity, but there is light output from the inside. So this means while the S21 and the matrix element, scattering matrix element. So if you read in some paper, you will keep saying S21, S21. Yeah, the S21 the element is B2 divided by A1, but A1 is 0. That means this S21 need to go to become a pole. Need to go to the implement. So this value need to be infinity. So that means its denominator is equal to 0. So again, this matched the lacing criterion of threshold if we decompose this beta into real part and imaginary part, that will give first exponential 2j beta f. The real part should be 1. So this is the criterion of the mode, optical mode. Second, exponential 2j beta L need to be 1/2 R1 R2. If you further deduce that, that will become the threshold gain should be internal loss plus mirror loss. So these two is actually, you will reach the same conclusion with different formalism. Okay, so the result is here. Okay, so if we only see we didn't consider about the optical gain or loss in the homogeneous medium. Let's only see what the diffraction effects happens in the Fabry-Perot element. The reflectivity, the reflectance of the power will be the square of the S11 square, and it will be a term like this. Okay, so this is really tedious. You just find the expression of this term and finding its conjugate. Okay, let it become plus and tie them together. So this is purely very tedious. I will skip that. It turns out the S112 will be 1 minus R plus 4 large R sine beta L. The device R1 blah 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 blah. Okay, anyway, just too long. Don't bother split that out. And the S21 is the transmission. It will be expressed as this one. So when does this single layer Fabry-Perot like etlon has the maximum reflectance? It happens when the sine beta L is 1. Yeah, because if it is 0, it goes to 0. So the larger value happens when the sine beta L is equal to 1. That means beta L should be the R number of half R number of pi. Then it is the Bragg's condition. The thickness should be 2n plus 1 lambda divided by 4n. For this segment, you will reach its maximum reflectivity with a single layer, and it will be 4r divided by 1 plus r squared. It is the case, the large R is this value. And the other case is when does you get a maximum transmission? It happens when the beta L is equal to integer of pi. Then this is a maximum transmittance, or this we can call it as the AR condition here. So in this case, the transmission will be 1. And if we plot the S11 and S12 with the beta L, here you will find you will have the minimum and the maximum at the corresponding position. Okay. Alright, so alright, so this is the Fabry-Perot. If you consider it has okay, I really try to tie them together. So the schedule, if we want to find the transmission matrix of the Fabry-Perot, we simply just times these 3 matrices together directly. It will feel a little bit painful while you're doing by hand, but this will be a very easy trick for computers. Yeah, you can set a lot of metrics. You will just directly go down the final result. But I think the computer will rather be difficult to treating a problem like this. Yeah, because your the formalism is not well defined. Okay, so if we directly times the 3 matrix of the interface 1 homogeneous medium 1 interface 2. Okay, that will create a relatively dense matrix at the first loop. But we can still see what's the special case. The first is that L is equal to lambda over 2n. Then the order beta L will reduce, and it becomes a real it's a real matrix with no phase delay. But if it's in a special case, if the beta is 0, it gives you a I everywhere. So you have a half of pi phase delay. The implication will be more strong in the next lecture while we're discussing about the DBR. Yeah, why we need a phase delay for half of lambda designs. Okay, so let's answer a question of the lecture here. If the reflectivity of the mirror 1 and 2 is not equal, and it's also not a special number like the same, or one is 1 and another is half, well, how much power should distribute from both phases? So the output power from phase 1, we just call it P1. Output power from phase 2, we can say we call it P2. And the P1 divided by P2 can be written down as the P1 squared divided by P2 squared. And what is P1? P1 is the power here, A1 plus times T1. And the B2 is A2 plus times T2. Just before leaving the interface. And we can further writing down the A1 as R2. Yeah, because you need to reflect here, then R2, then going here to exponential J beta 2. Okay. Then we can divide the common all the common term A2 here. Yeah, because we change the A1 as A2 times R and times the propagation. So the A1 becomes A2 R2 exponential J beta L. So I should make this as well. Okay, then we divide the both. The ratio is R2 squared T2 squared divided by T2 squared. And while later we know that the exponential to J beta L should be equal to R1, R2. Then P1 over P2, the ratio should be R2 T1 squared divided by R1 T2 squared. So the fraction of light coming from phase 1 will be P1 divided by P1 plus P2. And this is the total power. So you just put the part in, you will get the actual power coming from both sides. So let's see a special case. Let's see if the R2 is 1 and the R1 is 0. Well, R2 is 1, but R1 is finite. Some number less than 1. So if R2 is 1, let's see what happens. If R2 is 1 and R1, then T1 is 0. So this becomes equal. Then it becomes R2 T1. R2 is 1. And it's T2 is 0. Okay, so T2 is 0 here. So the F1 will be 1. All lights will coming out from phase 1. And if R2 is 1, then R2 is 1 and T2 is 0. Yeah, because there is no light transmitting from outside here. Then F2 will be 0. Yeah. So that will be because one of the homework will assume one is something like a 0.5 and the other is a 0.4. Yeah, you need to evaluate how much the light will coming out from both sides.